My name is Francis de los Reyes, and I'm the Glenn and Phyllis Futrell Distinguished Professor of Environmental Engineering in the Department of Civil Construction and Environmental Engineering at North Carolina State University. So what I study is wastewater treatment and global sanitation. And within wastewater treatment, I look at biological processes, microorganisms for um, treating and converting our waste to resources and energy, and also looking at the wastewater infrastructure globally. So the sanitation conditions and technologies that can provide access to sustainable sanitation around the world. The US has one of the most advanced water and wastewater and sanitation infrastructure in the world, right? If you think about, for example, quantifying it in terms of the Sustainable Development Goals, you will see the number for the US. Well, we have 99% coverage, so we're well above the target. But the reality is, if you think about the numbers, we still have issues. We have about 2.2 million Americans who don't have access to clean drinking water in their house and access to sanitation that actually treats their wastewater. The organization Dig Deep did a study and estimated that the cost to the US economy of those 2.2 million Americans not being connected or not having services is about $8.6 billion every year. About 75% of the US population is connected to centralized treatment systems. So what this means is that when you open your tap, you get clean drinking water. That clean drinking water is coming from a large reservoir, and that's treated at the water treatment plant and then transported to your house. And then that wastewater that you generate from your house is collected again through large sewer pipes. And then all of that goes to a centralized wastewater treatment plant. And that wastewater treatment plant treats that to a level where it can be discharged into a receiving body of water. So for 75% of the population, that is what happens. But then you have the 25%. So you're talking about tens of millions of people who rely on small systems, private wells, for example, or on-site systems like septic tanks for their wastewater treatment. And there you see a little bit of a disparity in terms of concerns and issues, because for these private well owners, we know that, again, about 25% of private wells are contaminated. And again, these are contaminants that affect public health. And then about 80 million Americans use septic tanks and cesspools. And again, for them, they're largely left to their own devices in terms of operation and maintenance and keeping it updated. There is a huge backlog in terms of maintenance needs and upgrading needs. So the EPA has estimated that over the next 2 decades, we need about $625 billion of investments just to maintain what we have, right? The pipes and the pumps and the treatment plants I mentioned earlier. More and more, we think of it not just as treatment, but really reclamation and reuse. So to the extent that we can actually treat it to the level where it can be used for irrigation, for example, then that requires another set of treatment. Basically, it's very important to make sure the water is disinfected and the pathogen content is very low. You're here more, more and more you're hearing about actual water reuse, and we divide that into potable use and non-potable use. So with potable use, what that means is, to the extent that it's actually clean enough so that it can go back to our drinking water system and can be used as drinking water. And that requires a lot more technology to make that work. You want to have multiple barriers against pathogens, against contaminants. And so you're really, really getting to the high levels of water quality. And that's been done in places like Singapore. You're hearing more and more in the West, San Diego and other states are testing and thinking about in the future having a system where part of your wastewater is treated for potable reuse. On the non-potable side, it's a lower level of quality because you're only going to use it for irrigation, for example, or for power plants or other uses that are not for human consumption. There's a movement in terms of wastewater treatment to separate out these different types of wastewater. And one way of thinking about this is you have yellow water, right, which is urine. You have gray water, which is the water from your sinks. And that's not as contaminated as the black water, which is basically the water from your toilets. So by separating these out, you can actually think about how can I treat them so that I can recover resources and energy. So for yellow water, urine has 80% of the nitrogen and 50% of the phosphorus in wastewater. By separating it out, we can think of ways of how we can recover that nitrogen and phosphorus and use that as fertilizer. So there's research going on there. On the gray water side, because that's the water from sinks, they are not contaminated with fecal material, at least not in very high concentrations. They're cleaner, if you will. Then maybe you need less treatment for that to be reused as toilet flushing water, for example, right? And then on the toilet water side, now that we've separated it out, it's more concentrated. Can we think of ways that we can more efficiently convert this to energy? There's an opportunity to actually have what we call decentralized or distributed water and wastewater infrastructure. So what that means is instead of pumping our wastewater hundreds of miles, long ways, millions of gallons per day to a centralized facility, maybe keep that water closer to home. And so treat the wastewater of a cluster of houses, think, a subdivision or 2 or 3 subdivisions. Or even at the level of the house, right? Maybe a house of the future of water where essentially the technology for recycling gray water, the technology for treating the black water are all in the house, maybe in your basement or in your garage. And so you're not pumping the water long distances, you're not pumping large volumes of water, and you can get energy savings right away. To really think about equity, we need to make sure that these underserved communities are receiving support. And when we think about designing solutions, that we think about these communities in terms again of either connecting them to centralized services or improving the state of these distributed or decentralized systems. The primary reason that most of them are not connected to centralized services is because it may be expensive. Like I told you about this, miles and miles of sewer lines or drinking water pipes. And the cost of these pipes and pumping large volumes of water, that's actually quite high. So if you think of solutions that are more scale adaptable, more decentralized, then we can reach more of these underserved communities. So that's one way, but we really have to be intentional about this because I think we have our focus on centralized solutions have left these communities behind. So if you think about equity, we have to think about who is this system for? Who are we designing for? and even to the level of how are we thinking about research, how are we thinking about training engineers. For the longest time, we've been training environmental engineers to design and operate and maintain these large systems. Today, we need to think about training the next generation of engineers to actually think about these smaller scale adaptable solutions